Hello everybody, good to see you all. I'll be talking about this tool called ParaSwift. So I'm from NetApp, and for those who don't know what NetApp does, so we provide storage solutions. It's a unified storage, NAS, SAN, and CIFS. So today I'm Rukma. I work for a team called Advanced Technology Group of NetApp. We are not a product group, but we are like a research group within NetApp. And yeah, so I'm traveling here from India. So let me take you through what ParaSwift is about. Okay, so let's start with the question of how ParaSwift can help, let's say, most of the people who are present here today. So if we look at the roles of a storage architect in a data center or a storage admin, right? On the left hand side, we have a few of these scenarios, right? And yeah, so these are like, some of the few scenarios that people encounter. Like for instance, you have a new application coming into your data center and you want to provision it, and probably you want to see that with the type of resources that you have in your data center, can I just fit in this application? Do I need to buy more servers or I need more compute? Probably not. Another thing could be like, for example, universities where you expect more number of students to come in every year, and the same application now needs to support more users. So can I just scale this application? Will this application just work for like 10x or 100x more users? Right? Or one of the objectives that everybody has is like, your total cost of ownership. Can I reduce it? Can I stop buying more equipment? Can I just do with the existing equipment? And at another scenario is migration. So you see that a new application is coming in, or the existing application has been suffering, and you want to migrate it elsewhere in your data center, and you want to see whether everything else will be fine. So typically what we see is that when you are into one or more of these scenarios, you typically have the problem of, you need to figure out, okay, what's going to be my new architecture? Am I going to design it and then go ahead and implement it in a way that I can just test it and see if the things are fine before you go into production? Right? And then you need a suite of applications on which you want to validate your infrastructure. So typically even at NetApp, when we say, oh, this storage server is going to be shipped for home directory workloads or backup workloads, we look at some kind of benchmarks, or we look at some kind of user inputs to see how does a home directory workload looks like, or how would a typical backup workload look like. But this is just a specification. There is nothing real out there. But in reality, when customers use our storage system for home directories or for backup, the workloads are very different. And that's when the problem starts, when the expectations in terms of performance probably does not match from what has been delivered. So ParaSwift is a toolkit, or it's a software which helps to in this category, that is, can I bring realistic field workloads into my testing even before I get into production? And the advantage of ParaSwift is it objectively helps you to reproduce or replay this workload. What I mean by objectively is that you don't have to set up VMs, you don't have to set up applications to see how they'll perform. But what I need from you is just a trace of the application, and I will reproduce with whatever hardware I have to make it more realistic as it can be. Okay. So this is like the bird's eye view of the ParaSwift ecosystem that we built. So I have a green line which actually separates, this is what we have in the paper, this is what we already have in our research team, which is based off RTP, the Raleigh. So what we have is, these are, let's say, the compute servers in the data center, or the VMs, or the applications, right? And this is, let's say, NetApp storage or any other storage to which the requests are going, and this yellow thing is the switch which is serving this workloads, right? So what we have is the capture appliance which goes and sits into the network, does a port mirroring on the switch, collects all the traces. This is right now limited to NFS v2 and v3. So collects NFS traces into this appliance, and this gives you a whole set of traces that we collect from our customers or internally within NetApp Now the next step is this tool. So what we do is, these traces are pretty humongous, as in if you capture traces for like a week, they would go into gigabytes, and if you continue capturing, they'll pretty soon go into terabytes. But more interesting question is, what do you do with these traces? I mean, you just can't keep them. You want to do something with them. So what we ended up doing is take this trace and use some statistical techniques so that we could extract out the important characteristics that are there in the trace. For instance, how many different file handles, or what are the characteristics of the IOs, how many are read, how many are metadata operations, what were the sizes of the files, what were the offsets at which the files were accessed, and we can see that all of these characteristics are very important if we want to repeat some of the performance characteristics or profiles on our servers. So all of this is neatly extracted out into a probabilistic statistical model, which is like a state machine. Right? But the advantage that we get with this kind of a modeling is manifold. So one could be, it actually allows us to compress the trace even further. So the entire trace is like compressed by another 95x, right? So you get a very small model, which is like a statistical model, which you can easily store. The other advantage is that when we typically capture workloads, and we have done it for a few of our customers, they are actually running huge data centers, like petabytes or even more, right? But if we want to test that out at a smaller scale, then the replay would not work. But since we have a statistical model, we can always tweak the model to say, oh, you got to scale it by 10 times smaller and replay it on a smaller infrastructure, but maintain those characteristics or those aspects of the workload live, so that we could regenerate those problems. So we do that, and in the process, what we have right now is the library of workload footprints. So you capture traces from home directories, you capture traces from animation workloads, you capture them from the backup workloads, and now we have footprints of all of them. So we could say, oh, this represents a home directory kind of a workload. Well, this model represents an animation workload. Now the next step is basically to go ahead and replay. So two things that you need for that. One is the workload characteristics that you are going to reproduce on the storage server, and this is not limited to NetApp, it could be any storage server, and that's the beauty of this work. Secondly, you need to understand what was the underlying file system layout, because when we talk about NFS, then we are talking about how many directories, the depth of the directories, number of files under directories, the sizes of the files under directories. So we kind of infer all of that here in the model from the trace, and we are able to regenerate or generate that image of file system onto the storage server, which is going to be under test. The second thing that we do is, in NetApp, we use this hardware called Load Dynamics. It's a Boston-based company, to actually test our systems at scale. So Load Dynamics is able to generate IOs which are SCSI requests, FC requests, NFS, CIFS, all of them, right? And we have written a plugin in this toolkit to convert this model into definitions that Load Dynamics can understand. So we could generate a project for Load Dynamics, import it into Load Dynamics, create the file system hierarchy beneath the server, and then run. So this is actually, as a short introduction to what this tool is. Let me go to the next slide. Yeah. So this is like the bigger box, which opens up, okay, what are the techniques that we actually put into to make the ParaSwift ready, right? So we have two pipelines within ParaSwift. One is called the inline pipeline, which is basically as the IOs or the NFS packets are coming into this software, we process each IO by IO, and then do some transformations on the trace. Right? And the other part of it is basically the offline component, which says, okay, well, we have observed traces for the past 1 hour or a day. Let's freeze it at this window and then take this statistics and build out a model. So this is like a batch processing component within ParaSwift. Okay, so I'll just give a brief idea of what kind of problems we deal with. So for example, when you capture a trace, there is a possibility that you might have lost certain packets. For instance, you see a packet which says read this file, and then you see a packet which says delete this file, and the third packet which says again read the file. So basically, where is the file? I mean, the file has been deleted and now you are trying to read on a file which is a successful operation. That means probably you have missed an operation which did a linking of the file or created a soft link or maybe recreated the file. So we kind of try to fill in those kind of missing packets heuristically in this block. Then another aspect of NFS trace what we have seen is that since we know the file handles at which the operations are happening, preserving the order of these operations becomes very important. For instance, if you are doing a make operation, maybe you are taking a lot of files and then you are combining them, and then a lot of intermediate files get generated and a lot of executables get generated. So all of these files are very important. So when you want to do a make like operation on the filer, you want to maybe you want to read all of these files, you want to do all of these operations on the files. So this is what we call as the workflow. So we do kind of heuristically estimate what kind of files or file handles are a part of a workflow and which are not. Also we try to look at, okay, what are the intensities of the various clients that you saw in the trace, and what was the concurrency level of the clients, that is how many different clients and each client how faster it was in each trace. And then we kind of infer all of this per IO level, and then finally put it into the offline component where it tries to finalize a lot of things, builds out a model, creates a file system hierarchy on the target that you want to run the workload, and then gives out a executable which you can then import in load dynamics and run. So this is in short the workflow of ParaSwift. So let me shift to in the benefit of time, we have the detailed algorithms and more comparisons in the paper which is out with the proceedings of the conference. To do the comparison, so what we wanted to do is we wanted to see how similar is the original trace with the trace that we have regenerated. So when you run the workload using load dynamics on the filer, you collect a trace back. So you have the original trace and you have the regenerated trace, and when you want to compare it. So some of the things that we decided to look at was the distributions. So we are talking about NFS, we are talking about whole lot of IO, that is read and write, and we are talking about various metadata operations like fstat and linking and things like that. We want to see how good or accurate we are in terms of emulating the operation mix, how good we are in terms of the reads and writes. So if the reads and writes are happening to various file handles, what are the different offsets at which these IOs were issued, what were the sizes of the IOs at which the reads and writes happened. So that is an important parameter that we look at. We also look at write properties, for instance, whether it was a new file creation, whether it was an append to an existing file, whether we were deleting a file and recreating the file. So we want to see how good we are in regenerating those characteristics as well. Well, a lot of performance issues are also reported because the writes does not happen at the block boundaries. So for example, NetApp uses this 4K as a block size. If the writing happens in the between a block or at the end of the block, then the whole block needs to be read. So it is called as like a misaligned write, right, which does not start at the block boundary. So we want to see how good we are in regenerating misaligned writes. And other things which are very important is like hot files, right? What is the working set of your workload and how soon the working set is changing? Are the top 20% or top 75% of the load generated by the NFS clients, does it restrict to how many files? Is it like 100 files? Is it similar in the case when you regenerate it? So that can we regenerate the pattern of performance problems in the replayed workload? And a whole bunch of things. So we use cumulative distributions of these different types of categories, and then we use something called as root mean square error to classify or quantify our errors. And what we found typically is that our errors are bounded within 92%. So we could be better than 92%, but we would have the error of at most 92% in most of the experiments that we did. This isn't just an example of the comparison. We have a lot of graphs in the paper. For example, we captured in NetApp the IT traces, that is NetApp IT, which supports all of our operations within NetApp, the DevOps, and we collected the traces for 2 weeks, and then we fed it to ParaSwift. and we replayed them, and then we compared the two traces. So what we see is the top two line graphs is basically the read workload, the red bar being the original read. So this is a period of 300 seconds, and this is the number of requests which were issued in each second, and then we try to overlay the red with the blue. So the blue one is regenerated reads. So this is how we were able to, I would say, recreate the pattern of reads. Of course, the configuration in this case was exactly similar as the configuration on which we captured the traces. So we were able to mimic it very efficiently, and this is a pattern of writes. So this is what I had, and this, I have a poster out there, and you're free to reach out to me if you have more questions. And do I have a time for questions?
We have time for one question.
Okay. Is there any question for me? Okay, I hope I've done a good job of explaining and you've got the essence of it. Thank you for listening.